So we're going to talk about how an electron actually moves if I put it in a piece of copper now. So imagine I have a piece of copper and I'm zoomed in real close, so each of those circles represents a copper atom, and the little green dot is an electron. And I'm going to apply an electric field to this guy, and when I have an electric field, that electron is going to want to move. It's going to want to accelerate, and it will accelerate based on the charge to mass ratio, because after all, QE is the force and MA is the force equals MA equation, so I get acceleration as Q over M times E. And since it's a constant acceleration, I can go ahead and solve for what V will be after some amount of time. It's whatever V was to start with, plus QE over M times T. Now the problem is the electron is not going to go too far before it actually hits something. It may run into a copper atom, it may run into some other stuff, impurities or dislocations or whatever. In any case, it's going to go a certain distance and then it's going to smack into something and scatter off. And it's going to keep doing this again and again, bouncing off of things as it goes. And what I'm going to do is propose to you that every time that happens, it on average comes to a stop. Now I know in fact it actually bounces forward and bounces backwards, but it's just as likely to bounce forward as it is backwards, so the average of the vector winds up being 0. And therefore I can say that the average velocity, I don't need to pay attention to the v0 term because it just adds out to 0. So the average velocity as a function of the field is going to be equal to QE over M times some value tau, where tau is the average amount of time it takes between each of those scatters. This is actually something that's a constant for different materials. It depends on the density and the amount of charge and a lot of different things. But in any case, tau is a property of the material, and it gives me what's known as the drift velocity, V sub d. We'll calculate this at a later time, but for now, this just tells you how fast on average an electron is going to be moving when I apply an electric field in this material, where the key things here are that Q is the charge of the electron, M is the mass of the electron, and tau is the time between collisions of that electron with other things that bring it to a stop. So now that I'm thinking about this, let's imagine for a second that it's your job to stand beside a piece of aluminum wire and count the electrons as they go by. So you're standing next to this wire. That's a cylinder that I've drawn across the screen there. I can't do it three-dimensional, but just imagine it's a round piece of aluminum there. And your job is to stand there and watch these guys go by. And over a certain amount of time, they'll drift forward because of this drift velocity I just talked about. Well, the number that you see pass is going to be contained in that green area there. It's as if you dropped a drop of ink or something and the ink flows forward over some amount of time. And that green area, that green volume technically, since this is a cylinder, is going to be given by the speed at which the electrons are flowing times the time you watch them, V sub d times delta t. Now if the density of electrons in this thing is n divided by v, and V is the volume of that green area, again, looking at it as being the cross-sectional area of the tube. That circle that I've got drawn out there represents sort of the cross-sectional cut of this cylinder of wire, times this Vd times T. It's basically the volume of a cylinder there. Then I can put these together and find that the number of electrons I'm going to see pass me is the density of electrons times the area times the drift velocity times the time. Now each one of these guys has a charge, of course, so I can calculate the amount of charge that passes by me as a function of time too. The delta Q I see go by is going to be equal to negative NEA V sub d delta T. Now the negative here is something I'm going to massage out in a second. It really just has to do with the fact that current really is not electrons flowing. We measure current going the opposite direction. As an electron moves to the right of the screen, we would represent that as a current of positive charge flowing to the left. It's sort of a subtle little thing that we probably won't have to concern ourselves much with, but it's worth keeping in mind. In any case, delta Q is negative NEA V sub d times delta T. Now, the rate at which these charges pass you is what we're going to refer to as the current. In other words, the delta Q over the delta T is something we'll identify with the variable I to represent the electrical current, charge per time. It's going to be given by negative NEA times the drift velocity. The current divided by the area is what's called the current density. In other words, how tightly packed this current flow is in that wire. So J, the current density, is negative NE times the drift velocity. Now, The drift velocity from the last page was QE over m times the scattering time, tau. And the Q for an electron is negative E, and that clears up my negative problem that I had there. So that the current density, J, is equal to NE squared tau over mu times the electric field. In other words, the current density is proportional to how strong the electric field is. And this kind of makes sense. The flow I expect to get of charges going through this tube, this piece of wire, is going to be proportional to how strong I'm giving them a push. How strong is the field? So, current density is proportional to field, and this is actually a really pretty critical phenomenon that's going to be an identifying topic of this chapter. Because what I'm going to do now is take that NE tau over mu and say that is specifically something for a material. N is the density of electrons, which I could calculate by, say, for instance, figuring out how many copper atoms I have in a cubic meter and assuming each one gives up an electron or whatever. E is the electron charge, which is a constant of nature. M is the mass of the electron, although in fact there's some games I have to play with that if I get into some serious solid state physics. And then tau is the scattering time, the average time it takes to scatter, which again is a property of the copper, how close together the atoms are and how big they are and things like that. So I can lump all those together into one constant. That constant is something I'm going to call sigma. It's what's called the conductivity. The reciprocal of that is rho, which is the resistivity. Now, what this means is I can rewrite this equation here as J is equal to sigma times E. And this is what's known as Ohm's law. Although it's not the Ohm's law that many of you may be familiar with if you've seen Ohm's law before. This is Ohm's law written on what's called a microscopic scale. This is true at every point, that if I go in and measure what the current density is at some point in that piece of wire and measure what the electric field is, they should be proportional to each other by this factor sigma. Now, remember again, we're looking at the charge drifting along as it goes. The electric field is there because there's a voltage on this wire. I've put some potential difference between one end of the wire and the other. So the field strength is just going to be that voltage divided by the length of wire. So I can replace E with V over L. I can also replace J with the current divided by the area. That's how we defined what the current density was, after all, how tightly packed the current was in a thin wire. So if I over A is equal to sigma times V over L, I can actually juggle this around and put all those constants into one spot. After I replace the sigma with 1 over rho, I find that I times rho L over A is equal to V, and this gets us to a somewhat more traditional view of Ohm's law, that V equals IR. The R in this case is what's known as the resistance of the wire, and it's equal to the resistivity rho times the length of the wire divided by the area. Now let me be clear about something here. Resistance and resistivity are two different things. Now conductivity, as we derived, was NE squared tau over mu. It's related to the properties of the actual material, and resistivity is just the reciprocal of that. So conductivity and resistivity are properties of the copper. It doesn't matter what shape I put it into. It is something that is what it is for copper or for aluminum or for glass or whatever I may be working with. Resistance depends on the shape. It is because I have a wire of a certain length in a certain area, or whatever shape it may be, a rectangular tube or whatever. So resistance is what an object will have, where resistivity is what the material that makes that object has. It's a subtle distinction, but it's something I really want you to be aware of. Now it's high time we said something about the units on these things, so let's look at those for just a second here. Current is going to be measured in a unit called an ampere. If I look at current, it was the change in charge over time, so it's a coulomb per second. And a coulomb per second we define by amperes, and the letter we use for that is a capital A. Now, it's a subtlety only a physicist would love here, but in actual fact, the ampere is the fundamental unit, is defined by international agreement. So a coulomb really should be taught as being an ampere times a second. It's somewhat more intuitive when you first learn it to think of the coulomb first, though, so it's not usually taught that way to begin with. But now that we know what both are, I'll go ahead and say that to you, and I'll explain later on why the ampere is considered the fundamental unit when we get into talking about magnetic fields. Another thing is resistance is measured in ohms. Remember that V equals IR, which means that R is equal to V over I. So a volt per ampere is what's known as an ohm, and we use the Greek letter capital omega to denote that. And resistivity would then be in ohm meters. Rho is equal to R times A over L. Actually, we can plug in the letters for that. An ohm times a meter squared divided by a meters gives me an ohm meters. Although quite frequently people will state these in ohm centimeters or other units, but the SI unit for it should be an ohm meter. So some sample resistivities here, just to give you a sense of scale. Silver and copper and gold, for instance, are very good conductors, and aluminum as well, and will have resistivities on the order of 1 times 10 to the minus 8 or so. Deionized water, on the other hand, is actually a pretty good insulator. It has a resistivity of about 1.8 times 10 to the 5th ohm meters. It actually is 18 centimeters, and in terms of measuring the purity of water, that's one of the ways of judging it, is to measure the resistivity. And when you get something that's close to 18 megohm centimeters, then you know that you've got very, very pure water. Finally, Teflon is a very good insulator. It's 10 to the 22 ohm meters. So you can see we've got a range of scales here about 30 ohm meters. That's quite a difference between things that conduct electricity well and things that don't. Now, just to give you one quick example of how we might put all this together into a problem, let's say I got a 16 thousandths of an inch diameter wire. That's a 26 gauge for those of you that are engineers. It's 20 centimeters long, so about the size of a piece of paper or so. It's connected between the poles of a 1.5 volt battery, so a regular battery that you might pull off the shelf. The question I'm going to ask is how much current flows through it. Well, first we need to calculate the resistance, because after all, I know the resistivity of copper. I just had it on that last slide, but I need to know the resistance of this particular wire. So I take the resistivity and multiply it by the length and divide by the area, and I get a resistance of 0.0259 ohms. This is a really crazy small resistance, and it's going to have an impact on our result in just a second that I'll talk about. But I want you to recognize that most of the time when you're dealing with real resistors, you would want to have something significantly larger than this to be meaningful. The other thing I'll point out about this is notice that the length of the wire, if I made it twice as long, I would have twice the resistance. So the length increases the resistance, but the area decreases the resistance. The area is down in the denominator. So if I had a larger diameter wire, then I would actually wind up with something where the resistance would be lower, because there'd be more room for the electrons to flow through it, if you will. In any case, now that I have R, I can use my V equals IR to figure out what the current will be. V divided by R gives me 57.9 amps. Now, there's a bit of a lie in this problem in the fact that the battery probably can't actually give me 57.9 amps. If I had a battery that really could store 1.5 volts and deliver that much current, it would do it, and it would probably actually fry this wire in a real big hurry because it would be too much power dissipated. We'll talk about that soon too. But in any case, if I idealize this, that would be the current that would flow. I'll talk about why that isn't really the case later on.